Good afternoon, everyone. Thank you so much for being here. I'm kind of nervous right now. I can feel my heartbeat, so please bear with me. Um, so today I'm going to be talking about this exciting project I worked on a few years ago called as computing geolocation from object shadows. So first off, I'm going to talk about the previous project that we worked on that led to the actual computing geolocation project. So this project was about time direction from image shadows. So the goal of this project was to give the algorithm the images of the object shadows, and it is going to give the estimated time at which those images were taken. And these are some of the images we got from the experiment. So first image is the actual image of the object shadow. The second one is just grayscale representation. And the third one, we get rid of all the noise surrounding that image. And the third image is the one that we feed to the algorithm, which is going to give us estimated time at which that image was taken. While doing research for this project, we came across this interesting paper. It was titled as Determining the Geographical Location of Image Scenes Based on the Object Shadow Lens, written by Professor Frode Sandnes. It was an interesting paper, and we thought maybe we are not going to get time to work on this because this seemed like a lot of work. Something happened in the summer. All my friends went for summer internship. I was looking for one for a long time, and then I could not get one, which wasn't really bad because if I had gotten one, I wouldn't be standing here giving this talk. So I worked on this project for next 2 months in collaboration with professor in my computer science department and actually the author of this paper. So I went through the paper multiple times, and there were some concepts we wanted to get familiar with. So first one was elevation of the sun. I didn't know what the elevation of the sun means. It's more like the angle that sun makes with the horizontal surface of the earth. So if you have an object, and if you place that vertical in the sunlight, and you get the shadow length, you have the object length, which is constant, but shadow length changes depending upon what time of the day it is. So elevation also changes depending upon when you're looking at that object shadow. So that was more like theoretical part. I also needed to build a simple equipment. So first off, you have to have the white paper so that you have to have something to cast the shadow of the object on. Then I used a refill, but you can also use like pen, pencil, or any vertical object. And then I had to use cardboard because you need to have some base to mount that object on so that it stands perfectly vertical. And then you have to have some device to take pictures of the object shadow. I had like ZT-160 back in 2012. It wasn't the best camera phone, but it actually served the purpose of the whole experiment. And then finally, this is how the whole setup looked like. Once it was done, I was so happy because I thought, it's so simple. Why was I so much worried about? Unfortunately, it wasn't true. It had like few challenges. Like when you mount the refill on the cardboard, you have to make sure it's perfectly vertical. Otherwise, you are going to get like false object shadow length. When you take pictures, you also have to make sure the camera is perfectly horizontal. And while taking multiple images, you have to make sure you maintain constant vertical distance. That time I didn't have tripod, so there were like a lot of sources of error in the whole process. And the whole process was highly dependent on the weather forecast as well. If it's rainy, windy, or cloudy, I could not perform this experiment on the outside, so I had to wait for a while. Fortunately, it was summer in Bloomington that time, so I was kind of lucky. And then I went through the paper multiple times, and then I had so many questions about it. How to choose increment steps and threshold that they describe in this paper? Or what kind of clock system does this paper use? Like, oh, you take images at this time, but how do I convert that into exact like timing, whether it's 12 hours or 24 hours? And then all the angles mentioned in this paper. Are they in degrees or radians? And if they're not, when and where should I apply all those conversions? Fortunately, I came in touch with Professor Frode Sandnes, who was the original author of the paper, and then Professor David Crandall, who was professor of computer science in my department. So actually, back to the experiment. So the first image represents the actual image of the object shadow I took. The second is the one with is a grayscale representation with a white background, some noise, and object shadow in the foreground. The third image is the one after getting rid of all the noise around that image. And third image is the one that we actually feed to the algorithm. So here we have the function compute practical elevation to which we pass the third image. We also pass the object length, which is constant throughout the experiment. And here we get the theoretical value of elevation. Once we get this value, we move on to the next step of algorithm. Here we have the function called as populate lat long. Here we pass the practical elevation value we got back from the previous experiment or the previous method. The declination of the sun, which depends what day of the year it is, we calculate that by another formula. We know the time at which that image was taken, and we also pass the array of locations so that we can populate all the potential values of locations at that place. And then we iterate over all the possible values of latitude and longitude. We calculate theoretical elevation, and we compare that with the practical elevation we pass to this method. And if these values are close enough, we add that latitude and longitude pair into location holder array in the form of point object. And this is just for the first experiment. And we repeat this experiment 2 more times on the single day, but at different times. We have to do that because just to get some more accuracy and confidence in the final values. So at the end of all this process, you have 3 text files which contains points in terms of latitudes and longitudes. But just looking at that data is not enough. You have to have something so that you can graphically see how those points look like. For that purpose, I use MATLAB. Actually, this was the last time I used MATLAB. I never got a chance to use that after that. But I liked it. It was pretty simple, and finally we got some representations at the end. So we read the text files, and we plot those points with the longitude on the x-axis and latitude on the y-axis. So the whole process looks something like this. You have 3 text files, which contains like pair of points. You pass them to the MATLAB script, and it creates beautiful pictorial representation like this. So ideally, we have to get like circle-ish shape. I know they are not perfectly circles, but so as long as they intersect exactly at 2 points, we are good. But it does not happen all the times. At that time, since I was living in Bloomington, Indiana, I thought it makes more sense to perform the experiment at the same place and see what accuracy do I get. Unfortunately, not all the experiments were success. Like, we got some of the graphs like this. You get like multiple intersecting points, which is confusing because I don't know like which are the 2 points I should consider. It happens because images were not taken properly or that they're not accurate. Some of the results were like this. You get 3 circles, and you also make them to intersect exactly at 2 points. There is longitude on the x-axis and latitude on the y-axis. There's one problem though. You get 1 value of longitude, but you get 2 values of latitude. And how do you know which one is correct one? The problem can be solved by using word map represented in terms of latitudes and longitudes. So if I say I get 2 values of latitude, say 8 and 1 is like 38. If I look at this map, the value of 8 means I'm somewhere in Central America, which I knew it wasn't true at that time. So I can say top point is the one that represents my actual location. And then if I compare that with expected value, they're pretty close, which is not so bad. And then this is the final result we got. We performed this experiment multiple times, try to get theoretical value of latitudes and longitudes, and try to compute accuracy in terms of their absolute differences. Finally, some observations and future improvements. In the future, if we can use tripod with better quality cameras, we can get better images, and then we can do better analysis, can get better accuracy at the end. It was also observed theoretically that if you perform this experiment on a day which is close to solstice, you get better results compared to the one which is close to equinox. And then basically the shadow length measurement algorithm we use, it was kind of complicated. Needed a lot of manual work and extra setup. So eventually, if we can improve that to detect shadow and calculate the length of the shadow programmatically, obviously this process can offer much better results. So if I consider all these factors, this experiment will provide much better accuracy in the future, and that is something I would very much like to see if I ever go back to experiment and try to repeat maybe in Boston where I live right now. And that's it from my end. Thank you so much for listening.